Our last video in our little series about tension refers to something called Atwood's machine, which you can see in the picture over here is really just a pulley with two unequal weights that are added to the system. And the idea here is this 10 kilogram weight is going to pull down more than this 5 kilogram weight can support, and then it's going to basically cause this to start to move upward. And the question is, what is the acceleration of the system once this is released? And you hopefully recognize that there are ropes attached to this, so there's going to be a tension T in each of these ropes. Now this is the same rope that goes from one side to the other, so it would be the same tension in each. But to find this out, we also have to know what the forces are on these things, and we have to do force diagrams or F net equations. And we'll start with the 10 kilograms. So they each get their own equation. So we're going to draw a free body diagram of the 10 kilogram mass. And you can say, all right, I know there's two forces that are acting on this. One is the weight pulling it down, and the other one is a tension pulling this upward. So there's our T. Here's our weight, which we know is equal to mass times gravity, which in this case it's a 10 kilogram mass, which would be 10 kilograms times 9.8 meters per second squared, which will just equal 98 newtons. So those are the forces that are affecting it, but we need to write this as an equation. Now to do that, we need to define something as positive or negative. So for our purposes, we're going to say things that make the system move in this direction, which means move this one up and this one down, will be positive. So going back to this now, we want to say, well, F net is going to equal mass times acceleration, which will equal, in this case, a positive tension T minus 98 newtons, or the weight. We can fill this part in if we need to, but for now, this is kind of our little, as far as we can go, mark. We found out the mass times acceleration using the 10 kilogram mass. This mass is 10. The acceleration is what we're looking for, because this will accelerate together, is equal to the tension minus 98 newtons. So now I'm going to switch colors and do the same thing for the 5. So I'm going to draw a similar box. It should be a little smaller, but it's not really super important to get that part. It's equal to the weight, which is mass times gravity again. In this case, it's going to be 5 kilograms times 9.8 meters per second squared, which will be 49 newtons, half of 98. And this one's going to be going up with the tension that way. Now we can change our positive and negative. We already defined the things that make it move in this direction will be positive. So I'm just going to simply say, all right, well, the net force is equal to mass times acceleration. Restatement of Newton's second law, by the way. So make sure we understand where that came from. Every force is equal to mass times acceleration. But now we know that those are going to be made up by these other forces, which will be 49 newtons, because that's going down in the positive direction, minus the tension. Now, because this tension is the same, I'm going to kind of dotly circle this. Dotly is my new word. Both of these are the same tensions. So what we can do is we can resolve this for tension. So I'm going to switch the color again. So in this case, my tension is going to equal, and I'm going to fill in this mass, which is 10 kilograms. 10 kilograms times A plus 98 newtons. I'm going to do the same thing over here, but this time I'm going to move the tension to this side. Tell you what, I'm going to go 5 kilograms times A, that's a K. Let me just try to clean that up a little bit with my eraser here. That's an ugly way to write that. Okay. 5 kilograms times A is equal to 49 newtons minus T. Now I want to get T by itself, and make it positive. So I want to put T over here is going to equal 49 newtons minus 5 times A. Okay? So now because these two tensions are equal, I can set 10A plus 98 is equal to 49N minus 5. So 5 times a. So now I can combine like terms. So I add 5 to each side, 5a to each side, sorry. And I will basically subtract 98 newtons. And I end up with 15 kilograms. I'm going to bring my label back in here. Times a is equal to 98 plus 49. Oops, that's a mistake, I'm sorry. It's a positive 49 minus 98, which makes that minus 49 newtons left over because one's half of the other. So now what I have to do is I have to divide each side by 15. Now I'm running out of room, but my acceleration is going to equal negative 49 minus 15 newtons divided by kilograms, which will eventually translate over to an acceleration. And when I do that, it comes out to be negative 3.27 meters per second squared. And that indicates that this actually would go the opposite way of our positive. And that should make sense. I probably should have defined this the other way. That's the direction that it will accelerate. It's going to pull down in the direction of the 10 kilogram mass, and this one's going to rise up. And it will move with the speed of 3.27 meters per second. So by using our F-net equations, we have two equations with two unknowns, but if we can solve for one of the unknowns, we can then go back and find the other. So if we wanted to know the tension now, we could take this 3.27, substitute it into here, and then solve for that and get the tension, which is a pretty easy thing. If you really want to do that, you could do that. So that's our tension part 3, where we use our F-net equations, or draw out our F-net equations to solve for an unknown tension, or in this case, the unknown acceleration.